In 2024, micropetrological laser scans of the Huashan and Longyou grottoes shifted the investigation from archaeology to geotechnical forensics. The scans stripped away the surface to reveal a raw, underlying structural geometry. The data mapped millions of square meters of continuous, parallel chiseled grooves. Every striation is cut at a mathematically uniform 60-degree incline, maintaining perfect alignment across the entire vault. When we isolate a single contact point, the math becomes problematic. To achieve this level of uniformity across a chamber of this scale, the builders had to maintain a material removal rate exceeding 2.4 cubic meters per day, per point. The host rock is Precambrian granite, which possesses a uniaxial compressive strength exceeding 120 megapascals. The mechanical energy required to displace 2.4 cubic meters of this material daily exceeds the structural limits of hand-driven iron tools. In this model, the metal fails before the granite yields. This creates a data gap. We are looking at a physical reality, massive structural pillars and concentric circular carvings that the known toolkit of the era cannot mathematically produce. To bridge this gap, we must audit the site through petrological stratigraphy, thermodynamic ventilation, and archaeoacoustics. This single metric of granite excavation suggests that our current technological baselines for ancient engineering are incomplete. The physical evidence outpaces the historical record of the tools. To understand the complexity of the granite grottoes, we first look at the geomechanical control group, the volcanic tuff of Cappadocia. This tuff is highly porous, with a compressive strength of only 10 to 30 megapascals. Its stability is governed by the Mohr-Coulomb shear strength criterion, where the rock's natural cohesive strength, marked here as C, is sufficient to support these wide-span arches without masonry. But that logic fails at the Barabar Caves in India. Here, the soft ash is replaced by a crystalline hard rock lithology. The Precambrian granite here has a compressive strength up to 180 megapascals and an elastic modulus of 70 gigapascals. It is one of the most abrasive materials on the planet. The traditional explanation for this excavation is fire setting. The physics of fire setting involves thermal shock. By applying intense heat, builders exploit the different thermal expansion coefficients of quartz and feldspar. The resulting stress generates microfractures, specifically along the grain boundaries, allowing the rock to be wedged apart. However, this process leaves behind a permanent signature, the excavation damage zone, or EDZ. It is a mechanically compromised, shattered Charters layer. But the Barabar walls show no EDZ. The builders removed the entire damaged layer and polished the granite to a mirror finish. This close-up shows a surface so flawless it effectively eliminates the grain boundary fractures used to carve the space. Mirror polishing granite serves a specific geotechnical purpose. It minimizes surface area and closes the pathways for chemical weathering. This indicates an empirical mastery of material science. The precision of the Barabar chambers isn't just visual, it is also acoustic. Mapping the interior reveals reverberation times exceeding 3.5 seconds, with the chambers functioning as resonant cavities, tuned strictly between 100 and 120 Hz. This wireframe demonstrates the physics of that tuning. Using the Rayleigh equation, we can see how the chamber's exact length, width, and height interact with the speed of sound. The architecture is shaped to generate standing waves that lock into this specific low-frequency range. This frequency has a measurable biological correlation. 110 Hz is the fundamental acoustic resonance of the human brain. In this clinical visualization, we see the effect of that resonance. The brain undergoes biophysiological entrainment. The high-frequency beta waves of normal consciousness synchronize and smooth into the slower alpha and theta waves, often associated with immersive sensory states. These specialized environments are known as sonotopes, zones characterized by a distinct and deliberate acoustic signature. We find this correlation at rock art sites globally. These rhinoceros paintings were positioned at physical nodes where acoustic echoes reach their maximum decibel strength. The rock curvatures act as efficient sound reflectors. The architectural data shows that these spaces function as high-precision resonators. The alignment between the room's dimensions and the human brain's resonance suggests these chambers were designed to interact directly with the listener's neurobiology. While the granite chambers manipulate sound, the multi-level cities of Cappadocia manipulate air. At Derinkuyu, the challenge was to maintain a stable environment 85 meters below the surface for 20,000 inhabitants. The solution was a passive system based on thermal buoyancy, known as the stack effect. This schematic maps the fluid dynamics of the master shafts. Temperature differences between the interior and surface create a natural pressure differential, forcing air to circulate in an autonomous loop, exhausting stale air through vertical shafts while drawing fresh air through the lower tunnels. As the seasons change, the temperature gradient reverses. The airflow direction seamlessly flips, maintaining a constant internal equilibrium of 12 to 15 degrees Celsius, regardless of the conditions on the surface. Sustaining 20,000 people underground requires a pre-industrial solution to complex fluid dynamic equations. It is an engineering feat that sits outside the expected capabilities of the period. To find the origin of this engineering, we have to look at the stratigraphy. One theory points to the Younger Dryas boundary, approximately 12,000 BCE. We can test this by looking at granular radiocarbon data from sites like Clogg's Cave. In this stratigraphic table, row XU21 marks a date approximately 12,500 years ago. At this exact depth, there is an anomalous organic spike, over 13 million phytoliths per gram of sediment. This metric represents a massive influx of human-transported plant material. It is a signature of intensive, high-density human activity in a deep cave environment. This organic presence accelerates chemical weathering inside the cave, as biological decay releases acidic moisture into the stone. This 12,500-year-old organic spike provides a forensic anchor. It places high-density human activity deep within the crust at the exact moment of the Younger Dryas impact, linking subterranean occupation to a period of catastrophic surface instability. Surface archaeology can only see the fragments. To map the true extent of these deep crust anomalies, we must use modern AI subsurface imaging. The current standard is time-lapse full waveform inversion. It exploits the complete seismic wavefield, amplitude, phase, and frequency-dependent dispersion. By analyzing that wavefield, FWI reconstructs high-resolution subsurface velocity profiles. It is our only way to see through the rock and locate ancient excavated voids. But even with our most advanced neural networks, interpreting this data is difficult. We are struggling with sparse semantics and interpretive non-uniqueness. This is the central paradox. We require terabyte-level datasets and AI interpretation systems just to detect these structures from the surface. Yet millennia ago, the builders executed them with perfect geometric and acoustic precision. This creates a literal gap in our linear historical models. If the 12,000 BCE anomaly marks the start of deep crust occupation, the architecture left behind operates on physical principles we're only now beginning to model. Full waveform inversion is the only empirical instrument we have to find what still remains hidden.